students, welcome back to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, today we are going to start a new chapter, that is thermodynamics. Okay, so this is a very important, I'll say, topic because very easy questions are being asked. So is it a very scoring topic, but many students find it difficult. But remember, for KCET you just need to remember certain formulas and certain theories, then definitely you can crack all the questions that is being asked in KCET, right? So yes students, and please join our WhatsApp channel, link is there in the description section. So this is going to be the part 1 of thermodynamics, where we are going to discuss thermodynamic terms and its applications. Okay, so without any further delay, let's get started here. So first I'll be telling you how are we going to complete this chapter. So we will be having 3 parts in this chapter. So in the first part, that is in today's lecture, we'll be discussing thermodynamic terms and applications. Second part will be more about measurement of delta U and delta H, enthalpy change, and in the third next one will be enthalpies of different types of reaction. So this is going to be a major topic here. Then in the third part, we'll be discussing about spontaneity and Gibbs free energy and equilibrium. Okay, fine. Now coming to weightage. So every year you can expect one question from this particular chapter. Okay, and that question is very easy and scoring. Okay, so now going to today's lecture, we'll be first discussing about thermodynamic terms. Okay, so what are the thermodynamics terms? We'll be discussing surrounding and system, types of system, state of system, and internal energy. Okay, next coming to applications, we'll be discuss about work, enthalpy, extensive and intensive properties, heat capacity, relation between Cp and Cv. Okay, these are the topics that we are going to cover today. So now coming to the first one, that is thermodynamic terms, and the first term that we are going to talk about is system and surrounding. So many of you might understand this from the word itself. So first of all, you see, system means that is part of the universe in which the observations are made. Now suppose you are doing the reaction in a particular beaker. Okay, so the reactions or whatever things are happening inside that beaker, or that beaker is considered as your system. Okay, what is surrounding then? Includes everything other than the system. So leaving that system, suppose you are doing in the lab room, the lab other equipments, everything else comes under surrounding. Okay, the point, the thing in which reaction is taking place, that is your system. Other than that, everything else is surrounding. Okay, that is the first thing. Next we have, so what I can say, this universe is made up of 2 things. One is system and the surrounding. Okay, universe and surrounding. Now there is something also called as boundary wall. Okay, boundary wall. What is boundary wall? It is something that separates system and surrounding. Okay, so these are the important definitions. What is system and surrounding? So where you are doing any reaction or anything, that particular system, that is the what where observations are made, that is system. Other than that, everything is surrounding. Clear? Next coming to types of system. So we have 3 types of system. Okay, just now we discussed type of system or system where we are doing the reactions or something. So now types of system is of again 3 types. One is open, closed, and isolated. Now what do you mean by open system? Open system means where you can exchange mass and energy. Okay, exchange both mass and energy. Now closed system means you can exchange okay, energy but not mass. I'll give you example of all the 3, it will be clear. And isolated system means cannot exchange mass and energy. Okay, now talking about the example. Now see, suppose exchange of mass and energy, suppose you are having hot water, okay, in an open vessel. Okay, what is the meaning of this? You are having a hot water in an open vessel. So suppose, so that means what, water will evaporate from there, right? When water is evaporating, mass is changing or matter is exchanged. Okay, better instead of mass you can also tell about matter. Okay, so matter is also exchanging here. okay, with the surrounding. Now suppose if I draw a diagram to make you understand here, suppose this is a beaker, okay, and you are having here hot water, okay. So now what happens, water is evaporating, so this part is your system, right, this is your surrounding. So you are exchanging matter with the surrounding, and also after some time you will feel that, you will find that this dish or this bowl has lost its hot, like that water has become cold. So where the heat has actually gone, the heat has gone to the surrounding, or the heat is transferred to the surrounding. You can just check, anytime you take a very hot vessel and keep it, right, after some time, after 3-4 hours, it will become cool. Why? Because it has given its heat to the surrounding. So that means what, here we can exchange both matter and energy. These type of systems are called as open system. Now what will I do, another, we will keep hot water, okay, hot water in a closed vessel. Now in this case what will happen, when you close it, okay, you have closed the lid, okay, you have closed this lid. So when you, if you have closed it, then what will happen here, this one will not evaporate, right, water cannot evaporate, water vapors will form, it will hit the lid and again it will condense there, right. So there is no evaporation taken, there is no loss of matter. So that is why here there will be no exchange of matter. But yes, this one also will become cold after so much time, right, after 2-3 hours this one will also become cold. That means exchange of heat exchange has taken place, okay. So that is what we call it as a closed system, where there is exchange of energy but no exchange of matter. Now if you think that this is a thermo flask, okay, now suppose this is a thermo flask, okay. If you have observed that in thermo flask the heat remains, or the water remains cold for 2-3 or even more than that, the better quality you purchase, the water remains cold inside, the water remains hot inside that. That means what, because it is closed, there is no exchange of energy, no exchange of matter, and because of its wall there is no exchange of energy as well. Yeah, after if like after 1 day, 2 day, definitely there will, that hot water will will also become cold, but for a certain period of time there is no exchange of matter as well as energy. Such systems are called as what? Such systems are called as isolated system, okay. Here I can give an example of hot water, okay, in thermo flask, okay, clear? Understood the 3 examples? Let us understand it again. Suppose you have hot water in an open vessel. In that case what will happen? Water will evaporate. So there is an exchange of matter between the system and the surrounding. Also that hot water bowl or vessel will become cold after some time. That means there is exchange of energy as well. Now if you close the vessel, then their water will not go out, but yes, energy will go out. That is called closed system. But if you take the same thing in a thermo flask, for a certain period of time there is no exchange of matter as well as energy. So it is an example of isolated system. Okay, I hope this type of systems are clear. Fine. Next, if we go state of a system, okay. So now what do you mean by state of a system? Suppose a system is there, okay, it will have certain, suppose you are standing here, okay. Now to tell your location or to tell about your position, we need to tell your location, where you are standing, what is the landmark there, right, something we need to define to tell your state here, right. Similarly, to tell about the state of a system, or state means condition of a system, we need certain parameters. Like for example, suppose here you want to tell, you will tell the location, okay. If you want to tell about the location, then you will tell, for telling location you can tell coordinates, right, what are the coordinates you are standing, you can tell the landmark, right. Now suppose you want to tell the physical state, okay, you can tell whether you are happy, okay, whether you are sad, okay, whether you are healthy, Okay, these are all things which can tell about your state or about your condition. Similarly, to tell the state of a system or condition of a system, we need certain parameters, and these parameters are called as state variables. Okay, so what is the work of state variables? They tell you about the state of a system. Okay, now again, what is state? State means, I mean here, condition of a system. Okay, clear? They will tell you about the condition of the system. Now, what are these state variables? So, we have pressure, volume and temperature. Okay. Now, here you should remember that we do not need all of them three to tell the state of a system. We can define any two and tell the state of a system. Okay. So, generally state of a system can be told by any two variables generally. Okay. Sometimes we need even one, sometimes it can happen even with three. Okay, so this is all about state of a system. Next we will come to work. Okay, next we will talk about internal energy. Okay, what is internal energy? So now see, the total energy of the system. In the system there will be particles, right? For example, you have taken sodium chloride solution. There are sodium plus ion, chlorine minus ions, right? They will be rotating. They have their vibrational energy, rotational energy, mechanical energy. So the total energy of a system, okay, how much, whatever type of energy is present inside that system because of the particles, this total energy of the system is called as internal energy, and it is denoted by capital U. Clear? What is total energy? What is internal energy? Internal energy is the total energy of the system that is present. Okay. Now, if you see here, now this internal energy of the system can be changed. Okay, you can increase the energy of the system, you can decrease the energy of the system, okay, by three ways, that is either work, heat or matter. Okay, so energy of the system can be changed by work, heat or matter. Okay, so now we will understand how we can change the internal energy of the system by doing work on it. Okay, by using work. Okay, so now you see one more thing. This is internal energy is a state function. Okay, we will define this after some time. Let us understand a case here. Now suppose you have a closed vessel, okay, and here you have some water. Okay, the temperature of this one is TA and the internal energy of the system is UA. Now you have a rod here. Okay, okay, now what you did, you churned it. Okay, you you churned the this stick, and as a result it rotated, and the energy of the particles there will increase. They will rotate, they will vibrate more rapidly, right? So now what happens, this becomes TB, temperature, and the internal energy becomes UB, right? So what I can say that the change in internal energy UB minus UA will be equal to, the change in internal energy will be equal to UB minus UA, right? Now what I did is, now second method what I did is, I did the same. Suppose here I did 5 joule of work by using my hand, I did 5 joules of work. Okay, now what you did, you gave the same thing to an electricity. Okay, you rotated this one using a motor till 5 joule of work is done. Okay, now you're getting case number 1 is what? Let me explain you properly. See here, case 1, case 1 is what? Using hand. Okay, now case 2 you did the same experiment. Okay, you put this one and this churn is there. Okay, and now you have water here. Okay, now this one you are using with a motor. Okay, so it is moving fast. Okay, so here you did 5 joule of work, here also you did 5 joule of work. Now you see the temperature, if you do the same 5 joule of work, it was initially TA, now it will be also TB only. Here it was UA, here also it is UB, right? Now here what we observe is, see, you reached from UA to UB by using hand, you reached from UA to UB by using electricity. Okay, the final point and the initial point are the same. it doesn't depend on how you reach from UA to UB. So these type of functions are called as state functions. Okay, state functions are those functions which do not depend on the path followed. It only depends on the initial and the final change. Okay, so now somebody if ask you in case 1, what is the change in internal energy? It will be UB minus UA. And if somebody asks you what is the change in internal energy in the second case, then also it is UB minus UA. But when you somebody suppose you are answering okay UB minus UA, in the second case also UB minus UA, nobody will be able to know that in first case it was through mechanical, through hand, and in the second one it was through electricity. You won't know that because the path doesn't play any role here. So those type of functions are called as state functions, and your U or internal energy is a state function. Okay, not only internal energy, there are many such functions which are state function, that is volume, pressure, temperature, these all are your state functions. Okay, so what is state function? Now I can define state function is does not, or let me write on this side. So I hope this is clear. What is state function? It doesn't depend on the path followed, whether you did by hand or you did with electricity. If you do the same amount of work, okay, then the same temperature will be there, and then we will have also same change in internal energy. Okay, so I can write here that state function means does not depend on path. Okay, now if we have this one, okay, now if I have this one, delta U or change in internal energy will be what? U2 minus U1 or UB minus UA is equal to work WAD. Okay, this WAD stands for adiabatic process. Now see, WAD means adiabatic work. Okay, now what does this WAD means here? Now see, when you did this churning and all, we took insulated walls, means there is no exchange of heat, and there is no exchange of heat between system and surrounding. Okay, so due to this, when you churned it, okay, when you churned it, obviously the temperature has risen for that particles, but the energy of the particles has risen. Now see, very simple thing. Now see, suppose this is the thing, okay, we have particles here and you churned it. Okay, now due to this the energy of the particles increases, right? But if it would have been a conducting wall, then what will happen? The rise in, suppose this is at low temperature, this became high temperature because of churning. So what would have happened? The high temperature to low temperature heat would have flowed, right? The temperature rise would not have been there. But what we did here is we took this insulated wall, or we call it adiabatic wall, due to which what happens? Due to this adiabatic wall, what happened? Whatever the energy was released when you heat it, when you churned it, right? The particles energy increased, right? Now due to this particle energy increase, heat was there, and due to this heat the temperature increased, right? The temperature or the heat did not flow out. So for this type of work when you do, this is called as work adiabatic or adiabatic work. So what I can say, what is adiabatic process? Adiabatic process are those where no exchange of heat, okay, between system and surrounding. Okay, there is no exchange of heat between system and surrounding. Got this one? Now coming to something called as sign convention. What is this sign convention? So we will see that. Now see, generally when work, okay, is done on the system, one second, work is done on the system, okay, in that case what will happen? Internal energy will increase, okay, and if work is done by the system, okay, in that case internal energy will decrease. Okay, now here what we are doing, when you are churning, you are disturbing the system, you are doing work on the system, so internal energy will increase. if work is done by the system, okay, if the work itself, if the system is doing some work, okay, if the system is expanding by itself, okay, suppose here one piston is there. Let me take one example. Suppose here we have this adiabatic valve, okay, and here we have a piston. Now what is this system doing? These systems are expanding, trying to expand by themselves to push the piston up. Okay, when work is done by the system, the internal energy will decrease, okay, because they are using their own energy. So by the system, internal energy will decrease, on the system, internal energy will increase, okay. So when you do work on the system, delta U increases, by the system, delta U decreases, okay. So this is all about internal energy. Let us revise once again. Internal energy is the total energy of the system, first point. Second point, internal energy can be changed by heat and by work, okay. Third point, internal energy is a state function, it does not depend on the path followed. Now fourth point, by work done, we can change the internal energy. So delta U is equal to U2 minus U1 is equal to work adiabatic, okay, adiabatic work. Now what is adiabatic process? A process where there is no exchange of energy between the system and the surrounding. Sign convention, work done on the system and internal energy increases, work done by the system, internal energy decreases, okay. Next, I told you we can change the internal energy by work and heat. So matter is also there, but the two major factors are work and heat. So let us now talk about heat, okay. So if you see here, a system with conducting walls should be there. First of all, we need to have a system with conducting walls, means that temperature should go here and there, the temperature can change, the heat can flow from system to surrounding. Now in this case what happens, delta U is equal to U2 minus U1 by is equal to Q, okay. So in case of, so what I am saying, if you have adiabatic system, okay, then delta U is equal to work adiabatic, okay. Now if you have this type of system where there is conducting walls, okay, in that case delta U is equal to Q, okay. How much heat you will provide, that much amount of internal energy will change, okay. So that is when you have, by heat you are trying to change the internal energy, okay. Now here also we have sign convention. So what is the sign convention? If so, Q stands for heat, okay, here Q stands for heat. Okay, what is the sign convention here? That if Q or heat is added, you are giving more heat, okay, then definitely delta U will increase, okay. Next, if Q is removed or heat is removed, okay, then delta U will decrease. Clear? This is there. Now one more thing that you need to know about internal energy is, internal energy is a function of temperature. Function of temperature. That means when temperature increases, internal energy will increase, temperature decreases, internal energy will decrease, okay. Now to increase or decrease this in temperature, you can use either work or heat. If you work is done on the system, temperature increases, internal energy increases. If heat is provided to the system, temperature increases, internal energy increases, right. So that is there. So now if that means if delta T, okay, is constant, or I can say delta T is equal to 0, means there is no change in temperature. If delta T is equal to 0, that means delta U will also be equal to 0. This is a very, very important concept that you should be knowing, okay. For delta T is equal to 0, delta U will be equal to 0, okay. Fine. Now let us go to the next thing, that is general case. General case means you are increasing the internal energy both by heat and work, okay. Not in the first case we thought only heat, second case we saw only work, but if you use both heat and work together, then U is changed by both heat and work, okay. In that case what I can say, the change in the internal energy will be equal to heat plus work, Q plus W, okay. So Q is your heat, W is work, okay. Delta U is equal to Q plus W. Now this equation is the mathematical expression of first law of thermodynamics. What does the first law of thermodynamics say? Energy can either be created or destroyed. Okay, energy is constant. Okay, so if you are providing, so the total energy of the system will be equal to the heat provided or work on it, heat and work. Clear? That is the first law of thermodynamics. Okay, now we will solve a very interesting question. This will help you to clear all your concepts whatever we have studied. Express the change in internal energy of a system when no heat is absorbed by the system from the surrounding but work is done on the system. What type of wall does the system have? Okay, now you see, we know that delta U is equal to Q plus W. We know this formula. Now what is it saying? No heat is absorbed by the system. If no heat is absorbed by the system, that means what? Q is equal to 0. According to this statement, Q is equal to 0. That means delta U is equal to W. Right? Now in which type of system, in which type of process there is no heat exchange? The name of the system, what type of wall does the system have? The system have adiabatic wall. Right? If you remember, in adiabatic wall there is no exchange between exchange of heat between the system and the surrounding. Okay. Next, coming here, the second one, no work is done on the system but Q amount of heat is taken out from the system and given to the surrounding. What type of wall does the system have? Okay. Now if you see the second one, okay, so this is the common equation, so I'll write 1 here. Okay. Now second one, what is the no work is done? That means definitely W equal to is 0. And what is about Q? Q amount of heat is taken out from the system, right? When Q is removed, I told you delta U will be negative, or that delta U will decrease. So I can say that delta U is equal to minus Q. Why minus Q? Because heat has been removed, or we can write that Q is equal to minus delta U. Now because there is exchange of heat taking place between the system and the surrounding, what type of walls we have? Conducting walls, or you can write thermal conducting walls. Thermal conducting walls. Okay, thermal conducting walls. Okay, next question number 3. Okay, W amount of work is done by the system. Work by the system means W is negative, and Q amount of heat is supplied to the system. Heat supplied means positive, right? What type of system would it be? So delta U is equal to Q minus W, right? Delta U will be equal to Q minus W. That you need to tell here. Okay, you have to express the change in internal energies. Delta U is equal to Q minus W. Okay, because Q you are providing, so plus Q, work is done by the system, so minus W. Okay, fine. Now let us go to the next thing, applications. Okay, work, whatever applications. Now whatever these chemical reactions are happening, what can be, what we can, where we can apply them and how we can apply them. Okay, so first thing is your work. So when a chemical reactions are happening, many gases are produced, right, and heat is evolved. So these gases, okay, can be used to do some work. Okay, the gases produced in the chemical reactions can be used for doing various types of work. So what is the so this, in this case, whatever gases are produced, that can do only pressure volume work, or we consider them as mechanical work. Okay, pressure volume work or mechanical work. So now suppose what happens, suppose you have a system, okay, and here you have a piston. Okay, a system with a piston. Okay, now here we have gas molecules. Okay, now suppose you pushed this piston down. Okay, you are doing some work on the gas molecule, right? You are doing some work on the gas molecule. So now what happens? What is the work done in that case? How can we calculate the work done in this case? So this type of process are called as irreversible process. What is meaning of irreversible process? So let me erase this one first. See, we'll do a very good diagram to understand this. So we have this one, okay, we have gas particles, okay, and here we have the piston, okay. Now what happens, suppose you want to press or you want to compress the gas up to this, up from here to here. Suppose you did it in one step, just you pushed it directly to this place, means the entire thing that you want to do you did in one particular step. That is called as irreversible process when done in single step, okay. Now in this case what will be the work done? Work done is equal to how much pressure you have applied, okay, P external minus V into V2 minus V1. So the original volume was, this is V2, this is V1, right, and here you are applying external pressure. So P external into V2 minus V1 will be the work done for irreversible work done, okay. Now if I want to calculate reversible work done, so the derivation is not required for your exam, so I have told you only the formula. Now what is reversible process? Now reversible process is like this. Suppose, okay, this system is at equilibrium, okay, with 5 weights, with 5 weights, okay, 1, 2, 3, 4 and 5, okay. Now you added one small weight here, okay, due to that it came up to here, okay. Then you added another small weight, then it came here, then you added another small weight, it came here. So these step from here to here, when it occurs in multiple steps, we call it reversible process, okay. So reversible reaction means it occurs in multiple steps, okay. Now here the work done formula is minus 2.303 nRT log V2 by V1. I'll be telling you the terms here. N is what? Moles of gas, okay. R is universal gas constant 8.314 joule mole inverse Kelvin inverse. T is what? Temperature, okay. V2 is what? Volume final, okay, and V1 is volume initial, okay. So that is reversible work done, clear, okay. Next we have one more here thing, that is about free expansion. I'll be telling you what is free expansion. Now see, if the gas is expanding, okay, the gas is expanding without any external pressure, means suppose you have this one, you have this container, okay, and here gas molecules are there, okay, and you are in vacuum. What will happen? You know, gas tendency is to spread, so gas will spread away, right, gas molecules will spread away and they are doing some work in that, but you do not have any external pressure in this case. So in that case P external is 0, so W formula is what? Minus P external into V2 minus V1. If P external is 0, then work is also 0. Then what is delta U formula? Delta U is equal to Q plus W, right, but work is 0, that means delta U will only be equal to QV or Q at constant volume, okay. So that is what you should know here, okay. I will erase these things, yeah. So clear this part. What is work done? We have irreversible formula, reversible formula and free expansion work done, okay. Next we will move towards isothermal process, okay. Isothermal process means what? What do you mean by isothermal process? Isothermal process means a process where temperature is constant, okay. If temperature is constant, that means delta T is constant, and I told you if delta T will be constant, delta U will be equal to 0. This is very important formula, very important, that whenever isothermal processes are there, temperature is constant, at that case internal energy change will be 0, okay. Now you can see here temperature is constant, so delta U will be equal to 0, okay. Now in this case, okay, if delta U is equal to 0 and you are doing some work, isothermal reversible work done is happening, okay. You are doing isothermal but irreversible work done. So in that case what I'll say, see, delta U is equal to 0, so I can say Q is equal to minus W, Q will be equal to minus W, and we know that W will be equal to P external V2 minus V1, right? Similarly, if isothermal reversible process is going on, isothermal again delta U is 0, Q will be equal to minus W, that is equal to 2.303 RT nRT log of V2 by V1. Okay, so this is there. Okay, next we'll go to the next thing, that is adiabatic change. Okay, so here I will write adiabatic change. So now if adiabatic process is there, okay, in that what happens, Q is equal to 0, so I can write delta U will be equal to W adiabatic, right? In case of adiabatic process, what is the value of delta U? Delta U is Q, okay, because sorry, delta U is work WAD, okay. Okay, so what all things we have learnt till now? See, we have delta U equal to 0 if temperature is constant, first thing, okay. Next we learn second thing, delta U is equal to Q plus W. Third thing that we learn is W2 formulas for irreversible and for reversible. These three things we have learnt till now, okay. All others are derived from here and there, but yes, these are the basic things that we learnt now. Fine, next we'll talk about enthalpy, okay. So now whenever you are exchanging heat, okay, if the volume is fixed, we call it QV, okay, but generally reactions does not take place at constant volume, okay, reactions takes place at constant pressure. So there is another term called as enthalpy, which means that heat exchange at constant pressure, okay. So delta H or change in enthalpy is equal to heat exchange at constant pressure, okay. Now this is also a state function, means does not depend on the path, does not depend on path, okay. Now what is the formula for this one? So for this one we have delta H is equal to delta U plus P delta V, okay. Delta H is equal to delta U plus P delta V. Now how PV, we know PV is equal to NGRT from ideal gas equation, so that we can write down delta H is equal to delta U plus delta NGRT, okay. This is written from P delta V, okay, delta NGRT. Now we will solve, see next one. Now this delta H is negative for exothermic process, means where the heat is released, and it is positive for endothermic process, okay. Next one more thing we have at constant volume, okay. So if you see, this is the formula for delta H is equal to delta U plus P delta B. At constant volume what will happen? This term becomes 0, so we have only delta H is equal to delta U, and delta U is nothing but heat exchanged at constant volume, heat exchanged at constant volume, okay. Now how am I getting this one? Now see, delta U is equal to Q plus W, right, and Q plus W can be written as P into V2 minus V1, right. If volume is constant, then this part will become 0, so I can write delta U is equal to Q. V represents that at constant volume, okay. So delta U is equal to Q delta V and QV, and delta H is equal to QP, heat exchange at constant pressure, okay. So here what are the two things that you need to remember? These formula you need to understand, okay, these two formulas. Now coming to the next thing, that is extensive and intensive properties. So extensive properties are those properties which depend on quantities, okay, which depend on the amount of substance present. For example, mass. Suppose you have 1 kg potato, 2 kg potato, right? The quantity differs, their mass will differ. So these type of properties are called as extensive properties. Example, volume, internal energy, enthalpy, heat capacity, these all are your extensive properties. Now what is intensive properties? Does not depend on the mass, volume, density, temperature, cm, that is molar heat capacity. Now let me give you an example. Suppose you have a container of water here, okay. Now what you did, you divided this into half, okay. So what is the volume of each container now? This is V by 2, this is V by 2, right. So when the quantity changed, volume also changed, right. But initially before dividing, the temperature was T, after dividing also the temperature will remain T, right? So that means what? Temperature does not depend how much quantity is present. Okay, so these type of properties are called as intensive properties, which do not depend on the amount of substance present. Okay, examples you can see here. Okay, next we will go to heat capacity. Next topic, very important. What is heat capacity? Now heat capacity, we have three types. One is heat capacity, molar heat capacity, and specific heat capacity. Before understanding this, let us talk about these terms. Now see, suppose you have water. Okay, you have a bucket of water and the temperature of that is 25 degrees Celsius. Now you want to make it to 26 degrees Celsius. You will provide heat, right? So the amount of heat that you provided to increase the temperature by 1 degree is called as your heat capacity. Okay, so what is heat capacity? Amount of heat required to raise the temperature by 1 unit. Okay, now what is molar heat capacity? Now suppose you are taking, instead of any amount of water, you are taking 1 mole of water. Okay, you are taking 18 gram of water, that is 1 mole. So when the amount of heat required to raise the temperature of a substance, of 1 mole of a substance by 1 degree is called as your molar heat capacity. Okay, amount of heat required to raise the temperature of 1 unit of substance by 1 unit. Okay, next, specific heat capacity. Specific heat capacity means 1 gram. If you are taking 1 gram of a substance and you are providing heat and you are raising its temperature by 1 degree. So how much amount of heat you need to give that 1 gram of substance to raise its temperature by 1 degree, that is called as specific heat capacity. Okay, so amount of heat required to raise the temperature of 1 gram of a substance by 1 unit. Okay, now coming to the heat capacity is represented by capital C, molar heat capacity by Cm, and specific heat capacity by small c. Okay, so now here how can we represent it? Q is equal to C into delta T. Okay, Q is equal to C stands for heat capacity, delta T is the amount of temperature that you have changed. Now see how this formula has come. Very simple. C is what? Suppose for example, for changing from 1 degree, for 1 degree we need 2 joules of energy or 2 joules of heat, right? For changing 4 degree, how much I'll read? 2 into 4, right? So this is what? Heat capacity, and it is what? The temperature change. So that is C into delta T. Okay, now if you change for 1 mole, then here you use molar heat capacity into delta T, and if you use specific heat capacity, we call MC delta T, where this C is your what? Specific heat capacity, capital C is your heat capacity. Okay, now we will see something, relation between Cp and Cv. Okay, what is the relation, how it has come, we will discuss now. Now see, here we have this formula first, that we know delta U, okay, is equal to heat exchange at constant volume, and delta H is equal to Qp. Okay, now this Qv is what? Cv delta T. Okay, Qv is Cv delta T and Qp is Cp delta T. Okay, now we have this equation, delta H is equal to delta U plus P delta V. For P delta V, I can write down RT. One second. See, we have this formula, delta Ng RT. Okay, now what I'll do, I'll take moles as constant, that is 1 mole, and I'll take temperature as variable. So how can I write this one? So we can write this one as, we can write down this one as R into delta T. For delta H, I can substitute what? Cp delta T. Okay, Cp delta T, then Cv delta T plus R delta T. Right, now these all will get cancelled. We have Cp minus Cv is equal to R. Okay, that is the relation here. Clear? Okay, so now we will do some practice questions. I know a lot of formulas has come, you might have got confused, but do not worry, we will practice a lot of questions so that we can get clarity about all the concepts and all the formulas. The first thing, which of the following property cannot be used to describe the state of a system? State of a system, remember, tells you about the condition of the system. Pressure, volume, temperature can tell, universal gas constant cannot tell because it is constant for all the systems, right? So option number D. Next, when work is done on the system or by the system, there is a change in. So we know internal energy can be changed by two ways, work and heat. So when you do on the system or by the system, what changes? Internal energy changes. Option number B is the correct answer. Okay, next, in an adiabatic process, the work done is 50 kilojoule. What is the internal energy? Okay, now you have this one. Internal energy formula, just remember one formula. What is saying? Adiabatic process means Q will be equal to 0. Work done is 50, means work is done on the system, that is 50 kilojoule, right? So that means what is delta U? So delta U is equal to 50 kilojoule. Okay, so correct answer here will be option number A. So now let us see the next question here. An open system allows the transfer of. So you know open system means where both matter and energy can be exchanged. So it allows the transfer of both, it allows the transfer of both matter and energy, okay, mass and energy. So option number C is the correct answer here. Now let us see the next question here, that is 6 liters of an ideal gas expands isothermally at a temperature of 300 Kelvin up to 10 liters, okay, at a pressure of 5 atm. What is the work done? So now here what happens, if you see what is the work done, so work done formula is equal to minus P external into V2 minus V1, right? So now if I see here, work done will be equal to, what is the external pressure here? 5 atm. So 5 into, okay, V2 minus V1. So I'll remove this one, okay. So V2 is 10 and then V1 is 6, 10 minus 6 is 4. So minus 20 liter atm. Okay, so now if you convert it, it will become Newton meter. So that is correct answer is option number D here, 20 Newton meter. Okay, so negative work is coming because it is expansion. Okay, and for compression the work will be positive. Okay. Okay, so here is a homework question for all of you. The value of the product of a universal gas constant and the temperature difference is given by 10 kilojoule per mole at 1 mole, and the internal energy is given by 20 kilojoule. You need to calculate the enthalpy of the system. Okay, so try this question, solve it and put the answer in the comment section. So thank you students, that was the end of the first part of thermodynamics. So see you soon in the next class with the most important, that is enthalpy calculations and all. So I hope you have enjoyed the class and do not forget to subscribe the channel.